In this video, we will learn how we can apply ant colony optimization to solve a minimization problem. So using numerical example, step by step, we will discuss how we can apply ant colony optimization to solve minimization problem. So what is ant colony optimization, how it is working, mathematical models, and how we can apply this algorithm to solve traveling salesman problem. We already discussed in previous videos. For more details, you can check the link given below in the description box. So right now we will not discuss the basic as we cover in previous videos. So we will directly apply this algorithm to solve minimization problem. So here you can see the minimization problem we have. Find the minimum of function fx. We have given a function fx that is x square minus 2x minus 11 in the range 0 to 3 using ant colony optimization method. So we will use here ant colony optimization method to find out the minimum value for this function in the range 0 to 3, and here you can see in previous video we find out the maximum of a function using particle swarm optimization. Now we will find out the minimum of a function using ant colony optimization method. Here you can see different steps used in this algorithm. First, initialize parameters. Next, initialize ants population. After that, calculate path selection probability by ants. Then we will apply here roulette wheel selection process for the path selection. After that, we will calculate objective function value for each ant, and then we will test the process convergence. If there is no convergence, increment counter, update pheromones, repeat step from 3 to 6. If there is convergence, then display the best solution that you found. Now step by step, we will see how we can apply this algorithm to solve minimization problem. So here you can see we have ants, then we have starting node that is home. Then you can see we have different path that ant can take to reach its destination, that is target as the food source. First we will initialize the parameters like population size, that is the total number of ants, decision variables, initial pheromones on the path, current iteration. So first we will consider n ants who will start the food search from home. So all the ants will start the food search from home, and they can travel by different path to reach destination, that is food source. So you can take here n ants. Value for n can be 5, 10, 100, 1000. It depends how many ants you want to use. So you can take any value for n. After that, ants will start food search and they can select any path to reach its destination. Now each ant can select only one path at a time. So for that, we will calculate the probability for the path selection for the ants using this state transition rule. After that, we have pheromone deposit, and the path visited by ant represent a solution. So once the path is complete by ant, they deposit pheromones on the path that we will calculate using this. After that, we will update the pheromones on the best path, that is the global best path. So when all ants complete the path, we will update the pheromones on the global best path using these equations. So now we'll solve the problem step by step. First, we will initialize the parameter. First parameter we have population size for the ants. We have for simplicity just 4 ants in the current iteration, and 1, 2, 3 and 4. We are taking here just 4 ants. You can take any number here. Next we have the design variable. You can take any value for this. So we are taking just one design variable. For this design variable, we will assume the discrete values from 0 to 3. So here we have 7 discrete value: x11, x12, x13, x14, x15, x16 and x17. And you can see we have different discrete values in the range 0 to 3. For x11 it is 0.0, x12 0.5. So here you can see these are the discrete values on path. Ants can select any of the discrete value, that is any path. Now we will assume equal amount of pheromones on each path. For simplicity, we will set the initial pheromone value on each path. It is 1, and here you can see it's 1. And j value for j we have 1 to 7, as we have here 7 discrete values. As you can see here, we have 7 discrete value. So we will initialize the pheromone on each path. Initially it is 1, so we have population size 4, design variable 1. Then we have initial pheromone on each path, that is 1. Then we have current iteration, it's 1. So we have 4 ants in the current population. Now we will calculate the path selection probability by the ant. So you can see here we have home, food source, that is the destination, and then we have different path. And you can see the discrete values on each path. So ant can select any path and travel from home to food source. For any ant, the probability of selecting path, that is the discrete value, we can calculate using this. Here, this is the pheromone trail, and you can see here, check if j belongs to nik. That is the set of neighborhood path for any ant k. As you can see here, we have the home node, and here we have the destination, that is the food source, and in between we have different levels, level 1, level 2, level 3. Ant will travel through the different levels to reach the destination. So here the nodes visited by ant is considered as the potential solution, and ants can travel through different layers. For example, in traveling salesman problem, we have n cities and we are using n ants to find out the shortest possible route for the salesperson. So here you can see we have number of nodes, a number of levels. So we're using this to prevent ant from returning to the same path. So ants move from node to node until they reach the destination, that is the food source. So for any ant, the probability of selecting the path, that is the discrete value. That is the probability of selecting the discrete value that we can calculate using this. Here you can see this is the initial pheromone trail, that for simplicity we are taking 1 for the first iteration. You can see the value for p we have 1 to 7, and value for pheromone. So you can see 1 1 is 1, 1 2 is also 1, 1 3 is also 1. So summation of all this we have 7. Now we have probability for selecting the path is 1 by 7. So now we are going to determine the path selected by the ants. So first we will generate here 4 random numbers. We have 4 ants, so we will generate 4 random numbers. They are the normally distributed random values in the range 0 and 1. First random number for first ant, second random number for second ant, third for the third ant, fourth for the fourth ant. After that, here we will define the intervals based on the probabilities. Selection probability, that is 1 by 7. Now we will define the interval based on the probabilities. We will create here the intervals for the roulette wheel selection process. So x11 we have 0 to 1 by 7. So the interval we got here for x11 0.0, 0.01428. 1 divided by 7, that is 0.1428. Next we have x12, that is 1 by 7, and here we have 2 by 7. Then we got the interval for this. Like that we have for x13, x14, x15, x16 and x17. You can see here it is 1, so stop. You can see here 0 to 1, we define all the intervals for the path selection. Here the width of each interval should be proportional to the probability associated with the path. So now we have all the intervals. Now we will select the path. So we will check in which interval the random number falls in. So here you can see we have 4 random numbers. Now we will assign one random number to each end. So we will assign here first random number to first end, second random number to second end, third random number to third end, fourth one to the fourth end. Now we will select the path for each end. So how we will select this? We will check in which interval this random number falls. So first we will check for the first end. For the first end we have random number 0.3122. Now in all intervals we will check where this falls. You can see for the first end it is here in x13. This value falls here in between this interval. For the second end you can see here value we have 0.8711 and it falls here in this interval x17. For the third and third random number it falls in this interval, that is 0.4729. You can see here fourth random number is false. Fourth random number falls here in x15. So they are the path selected by the end. So first end selected the path x13, that is the discrete value, it's selected here. Second end selected x17, third end selected x14, and fourth end selected x15. So here you can see each end selected now their path to reach. Now they will travel from this path. So you can see each end selected their path. Now they will travel from home to food source. For the first end we have this path x13. For the second end x17, that is 0.3.0. For the third end it is x14, that is 1.5. For the fourth end we have x15, that is 2.0. Now we will calculate the objective function value here, and then we will select the best and the worst value, and we will consider the minimum value as the best value and maximum value as the worst value. Because we are doing here minimization, so we will consider minimum value, best, and maximum worst. So now we will use this function and find out the minimum value for each end. So here you can see for the first end we have the objective function. Put the value here. For the first end we have 1 point. Here you can see value for each end. Put all these values in the objective function. We have 1.0. Put the value here in this objective function and we got the value minus 12.0. Second end value we have 3.0. Put this value in the function and we got the value for this end minus 8.0. Third end value we have 1.5. Put this value in this objective function and we got the objective function value minus 11.75 for the third end. For fourth end we have the value 2.0. Put this value in this objective function and we got the objective function value for fourth end minus 11.0. So you can see now we calculated the objective function values for first end minus 12.0, for second end minus 8.0, for third end minus 11.75, for fourth end minus 11.0. Now we will select the best path. So best value is the objective function having the minimum value. So f best, that is the best fitness value, it is minus 0.5. In position, that is x13, and worst one you can see here it is second end, that is minus 8.0 fitness value, and position we have, and discrete value for this we have x17, that is 3.0. Now we have the best and the worst solution. Now we will check the process convergence. So now we will test process convergence. So here we will check whether all ends choose the one best path or not. Right now you can see there is no convergence because all ends selected different route, and the best route we have for the first end only and other end are on the different route, so there is no convergence. So when there is no convergence, we will assume that all ants return to home and they will start food search again. Now all ants return to the home. Now again in the second iteration they will start food search, update pheromone and all. They will again start the food search. We will repeat this process until convergence. Convergence means the best route that is selected by all ants. Until we will repeat the process. So here repeat the process now. Increment counter, current iteration 2, update pheromone. Initially we use pheromone 1 at each path. Now we will update this value. You can see here using this equation we can update the pheromone. Here this is the remaining pheromone from the previous iteration, or we can say this is the older pheromone value. So it represents the remaining pheromone from the previous iteration after evaporation. So after some time pheromones evaporate, so we calculate this value using this 1 minus rho, and here rho is the evaporation rate. We have 0.5 to 0.8. Next you can see here, so we can calculate the remaining pheromone from the previous iteration after evaporation using this equation. 1 minus rho value we have 0.5 to 0.8. We are taking this 0.5, so put the value here and we got here 0.5. After that you can see here summation sign. You can see here this is the pheromone deposited by the best ant that we can calculate using this equation. Here you can see the pheromone deposited by best ant. We have a summation. It represents if multiple ants take the same best route, then we will calculate this using this. So right now we have just one ant that took the best route. So here we will put the ant. So here we will put the best ant fitness value. We have minus 12.0, and the buzz we have minus 8.0, and here this is a constant value. So we got the value for pheromone deposited by best ant 3.0. Now we will update pheromones, that is older plus best ant. So we have one best ant. So we have one ant that took the best solution. So for that route we have 1.0 plus the best ant we have 0.3.0. We got 4.0. So this is only for the third route, that is the best route selected by ant. And here you can see for other route, for route 1, for route 1, 2, 4, 5, 6, 7, we have the pheromone value 0.5. So you can see here. So you can see here first ant took the third route, that is this one. So this is the best route. So we have the pheromone value. So we calculated different value for this route, and for other route we have different pheromone value. So this is the best route. So we have high level of pheromones on this route, that is 4.0, and on the other path we have pheromone 0.5. After that we will repeat the step 3 to 0 because there is no convergence. And here again calculate the path selection probability by the ants. Again for any ant we have the chance of choosing the path is calculated. Now we calculate the probability of selecting the best path and the other path. So probability, so best path we have the third one P13, and other we have P11, 12, 14, 15, 16 and 17. So probability for selecting the other route is here this one 0.5, that is the pheromone level on this path divided by 7. We got this value. And then the probability of selecting the best path we have here this 4.0, that is the pheromone level on the best path divided by 7. So we got here the value for this route 0.5714. Now again we will create the intervals for selecting the path. For the first one you can see here how. Now this time for x11, so path x11 equal to 0 to p11. We can see the p11 value we have 0.0714, this one. Then x12 it is p11 comma p11 plus p12. So p11 is 0.0714, p11 plus p12. you can see the P12 value again 0.714, and put the value here. Then for the third, then for x13, then for x13 it is P11 plus P12 comma P11 plus P12 plus P13. Put the value here. Right now you can see the P13 value we have 0.5714, and same for the x14, P11, P12, P13 comma P11, P12, P13, P14, like that for the x15, x16 and x17. You can see range from, you can see here range from 0 to 1. All the values are in between 0 and 1. Now again we will generate 4 random numbers. So here they are normally distributed between 0 and 1. After that we will check in which interval the random number falls. You can see here first random number we have 0.3688. Check where it falls. It falls here, that is third and again selected third path. Same process we are repeating here. Check where these random number falls. So when you will check in the result, you will see first and selected x13, that is 1.0, second and selected x16, value we have is 2.5, third and selected x11, that is 0.0, and fourth and selected x13, that is 1.0. Right now you can see here 2 and selected 1 root, that is the best root x13. Now we will calculate the objective function value for each ant using the objective function. So in that objective function, put all the values here. For ant 1 we have 1.0, for ant 2 2.5, for ant 3 0.0, and 4 it is 1.0. Put all the value and you can see the objective function value. And you can see here for first ant we got the objective function value minus 12.0, for second ant minus 9.75, for third ant we got the objective function value minus 11.0, for the fourth ant minus 12.0. Now we will select the best and the worst. So here among all you can see the best position. Again we have the third path x13, value we have 10, and in this iteration 2 and selected 1 best path. So we have f1, f4 is minus 12.0. And the worst case we have here for second ant x16. For the second ant, that is again the worst solution 2.5, and the fitness value for this we have 9.75. Now again we will check the convergence. We will check whether all ants select the one best root or not. So right now again there is no convergence because right now only 2 ants, ant 1 and ant 4, they selected one root, that is best root, but ant 2 and ant 3, you can see, but ant 2 and ant 3 they selected different root. So we will repeat until all ants selected the one root, that is the best root. So again here there is no convergence. Increment the counter. Now we have third iteration. Again we will update the pheromones. You can see now we have 2 ants, 1 and 4, ant 1 and ant 4. So put the values here, and then we got the, and then update pheromone. So now we will update the pheromone here using this equation. So we have best path and non-best path. For best path there is j equal to 3, that is the third path. You can see older pheromone value 4.0 plus we will put the value here 4.931, and we got the new value for this. And for other path we have older value 0.5, so calculate this and we got new pheromone value for the other part 0.25. So we have now pheromone, so we have new pheromone value for the third iteration. For the best path it is 8.9231, and for other path we have 0.25. Now again we will calculate the probability for the ants to select the path. So here you can see we have the pheromone values. So probability value for the third path we have 0.8561, and the probability value for the other paths we have 0.0240. You can see here we calculated. So probability of selecting best root is 8.8561, is 0.8561 and probability of selecting other route you can see 0.0240. Now again define the intervals based on the probabilities. Here you can see we define all the intervals, and then again we will take 4 random numbers and repeat the process. And check if there is convergence or not. If there is convergence, then display the best solution, that is the best path. If there is no convergence, then again return the ants to home and start search again. So we repeated. So right now we did the calculation till 2 iteration and we got the best route, that is the x13, and it is selected by 2 ants. You can further continue the example and you can see where the convergence, so at which iteration it converges, and find out the best route by all ends. So that's all about this video. Here we find out the minimum value for this function in the range 0.3 using ACO method. So you can further continue this example until convergence. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.